Hi there. Thank you for clicking on this video. In this lesson, we are going to talk about rational exponents. Please like this video lesson if you find it helpful. Subscribe to the channel for more math content and check out the practice set for this lesson so you can check your mastery of the concepts that we cover. Now, a question you might have is why cover this before covering multiplying radicals? And if you're watching the videos in order, which I know some of you aren't, some of you just do a search like show me, rational exponents. But if you look on the channel in the order that the videos are, it's adding and subtracting radicals and then rational exponents and then multiplying radicals. And that might seem like an odd order. Why wouldn't we do like all the operations on radicals in one go? Well, that's because rational exponents connect exponents to radicals. So we actually have this connection between these two concepts and allow us to transfer what we know about exponents to apply to radicals. So basically what happened was I started drafting a lesson for multiplying radicals and was unhappy with the fact that I would just be giving a rule with no rationale behind it. I'm so big on like not memorizing random rules and instead focusing on the underlying concepts of why the rules work. Thus, our rules for multiplying radicals are better grounded if we can rely on our knowledge of exponents. And I'm all about grounding our knowledge. If the concepts we're covering make sense, then you're more likely to remember them. So what do we already know? Every lesson, and if you've watched others of my lessons, I like to always present new content in the light of old content. What do we already know about numbers or algebra? Well, we know that a square root undoes squaring. Okay, that is what a square root is. And we're going to begin with square roots and then we'll generalize it. So for example, the square root of x squared is equal to x. And you might recall from studying radicals that there's actually an index on that radical indicating that it is a square root. And so if you have x and then you square it and then you square root it, you will come back to the x. In other words, the exponent and the radical undo each other. And it would also work the other way around. The square root of x squared would behave the same way. If you have x, and then you take the square root of it, and then you square that, it will bring you back to x. So I want you to remember that fact, okay, that a square root undoes squaring. And we also know that when we raise a power to a power, we multiply exponents. So this goes back to Algebra 1 and what we call like the laws of exponents. And there's quite a large collection of things that qualify as laws of exponents. And at least the way I approach it, I really am only big on covering 2 or 3 of those laws in Algebra 1 and then covering the rest of them in Algebra 2. But I think pretty much everybody does cover this in Algebra 1. And here's what it is, what we mean by raising a power to a power. So if I have x to the third and I raise that whole thing to the fourth power, that would give me x to the 12th, meaning we multiply the 3 and the 4. And if you'd like a quick refresher on that, x to the third raised to the fourth power, well, that's x to the third times x to the third times x to the third times x to the third, because that's what's being raised to the fourth power. And that's going to give me 3 x's, and then 3 more x's, and then 3 more x's, and 3 more x's. And we realize, oh, wow, I've got x times itself 12 times in there. So it's x to the 12th. And that would work all the time. And then what we have here is the general rule. If you take an exponent, raise it to an exponent, you would multiply the exponents. So I want you to keep those 2 things in mind, that when we square a square root, we get x, that they undo each other, and this particular law of exponents. Now consider this. Suppose we had an exponent that was a fraction. Now that is stepping into like the new territory. So our definition of an exponent is typically at this point, it tells you how many times something is used as a factor. Sorry about that. And it doesn't make any sense that the exponent would be a fraction. But let's just suppose that it was. How could we figure out what that exponent meant? Because it really does not fit in our definition of what an exponent should be. How can x be used as a factor like half a time or 2/3 of a time? Well, we'd like to figure out what that means. So let's look at an exponent of 1/2 as a trial case. So suppose you had this, you have like x to the 1/2. Now, we're going to start with the 1/2, and then we're going to generalize this. So x to the 1/2 squared. Okay, so we have this x to the 1/2, and now I'm going to take that x to the 1/2 and I'm going to square it. Now, I do know what exponents do. When we raise a power to a power, we would multiply the exponents. So right here, this would be x to the 1/2 times 2. I have no reason to think that my laws of exponents would not work. And now this becomes a problem of, well, what is 1/2 times 2? Well, 1/2 times 2 is 2/2 or 1. So that would be x to the first power or simply x. So I want you to take a closer look at that. If I have x to the 1/2 and I square it, that will give me x. Okay, because of the laws of exponents. So what can we conclude? I know that the square root of x, when I square it, gives me x. But now I also know that x to the 1/2, when I square it, gives me x. So just kind of take a look here. We've got the x's are the same. We've got the equals are the same. We have the squaring is the same. Therefore, the thing that is being squared must also be the same. So x to the 1/2 right here must be equal to the square root of x. X to the 1/2 must be equal to the square root of x. Now, if you're not familiar with that symbol right there, that is math symbol for the word therefore. You can use that in a math class anytime you want. It should be recognizable. I'd be surprised if your math teacher did not recognize that. I'm not going to vouch for every math teacher out there. My students can use it. I would not use it in an English class though. So therefore, x to the 1/2 must be equal to x squared. And what we've done there is we've developed an argument or a rationale for what that fractional exponent means. That fractional exponent is the equivalent of a radical. Now, can this be generalized beyond square roots? So we start with square roots because that's the root or radical that we're most familiar with. We've done the most work with over the years. Can we generalize this to cube roots, fourth roots, maybe other kinds of exponents? Like what if you had an exponent of like 2/3? So it wasn't 1/3, it was 2/3. Like, can we do that? Well, of course we can. We can generalize that. So bear with me. We're going to go through the generalization so you can see where it comes from, and then I'll summarize it into the sound bite, which is where I don't want to start. I don't ever want to just give you guys a fact and say, here, memorize this, and here's your little algorithm for answering these kinds of questions. Like, we want this to make sense. We want it to be grounded. That's going to empower you to go further with it. So let's go with m's and n's. So here I have the nth root, and I'm raising it to the nth power. Okay, so I'm going to go and highlight that. We want to be able to focus our visuals on the right things. So we have the nth root, and we're raising it to the nth power. And we know that those would undo each other. Just like a square root and squaring undo each other, a cube root and cubing would undo each other. A generic nth root, pick whatever number you want, the fifth root, and we're going to raise it to the fifth power. Well, it is going to undo itself, and we are going to be left with, if I can find my pen, x to the nth. Okay, that's going to give us x to the nth. Now, in the next line down, we have something similar. Okay, so we have our rational exponent. And again, notice what's the same. I have the equals the same. I have the ends the same. X's are the same. Now, what's different is this right here, but kind of bear with me. I have an exponent being raised to an exponent. Now, if you're having a little bit of a hard time seeing that, I'm going to rewrite it up here in the upper right. What we're looking at is not that. Try again. X to the m over n raised to the nth power. So the program that I'm typing in, which is equation editor, there's just not a great way. It looks like really clunky with the rational exponent. So it might help you to see it. So that's what we're looking at. And we know that we multiply exponents. So this is x to the m over n times n. Well, that is if I divide by n and multiply by n, those are going to cancel each other out, leaving me with x to the mth power. Therefore, these two expressions must be the same. And we can do the same thing we did before. If we have the following things the same, so we've got x to the mth, that's the same. We've got the exponent of n is the same. Therefore, let me erase this. Okay, therefore, these two things, grab a different color highlighter, must also be the same. So the nth root of x to the m would be equal to x to the m over n power. Therefore, here we go. Write it out. Here we go. X to the m over nth power is equal to the nth root of x to the m. And it's that same reasoning that we established with the square roots, but now we've just generalized it. And typically in an Algebra 2 class, a lot of teachers, including myself at many times, I've been teaching for a very long time, I would just give students this, or maybe do a little exploration on the calculator to try to draw some connections and just say, here, you have to memorize this. But it's really, really good for you to see where it comes from, that this is reasonable, and it's going to increase your chances that you remember it, or if you forget it, that you could kind of refigure it out. Now, why is this so important? This kind of circles all the way back to the beginning of the lesson. It ties together our study of radicals to our knowledge of exponents. What we know of how exponents work can now be applied to radicals. So if we get stuck on something with radicals, we can convert them to exponents and maybe do something with those exponents that we couldn't do before, or vice versa. It opens up a whole new toolkit. So we're no longer stuck in a unit on radicals. Now we have brought exponents into that, and it can give us a whole other way of looking at it. Several years ago, I was teaching, and I think it was radical equations, and I would teach them one particular way using like undoing a radical. And I had a student who basically got stymied on it. And anyway, actually what that student did was he converted stuff to exponents and did it a totally different way than the way I taught it. But it was so well laid out. And what it showed was he was able to pull in other knowledge to be able to solve something. And that is critical. Now, one final useful fact, okay? We are almost done with this lesson. This is a very short lesson. This is also true. So the nth root of x to the m is equal to the nth root of x all raised to the m. Okay, and just notice the difference there. It's the placement of the m. So that exponent could be under the radical, or it could be outside the radical. Now, the placement of the m actually doesn't matter. This feels counterintuitive. In math class, if you've been in math class any length of time, which if you're watching this video, you have been, then you know that we just can't move stuff around willy-nilly. Like the placement of an exponent matters. The placement of things in the slope formula matter. You can't just switch numbers and move stuff around because you don't like where they are. So why are we allowed to just move that m outside? And the answer is going to come from doing the exponents out. So let's take a look at why that's okay. So I'm going to start with this expression right here. And I'm going to use what we just established, which is that is equal to x to the m over nth power. Okay, and so we've already established that that is true. Now, within that exponent, I am going to do this. So you just kind of watch. I am going to say that that is 1 over n times n m. Okay, and I want you to just kind of look at that for a second. And so that you're convinced that that is actually a true thing. Okay, and if you need a little help, okay, if you have 1 over n times m, well, m is equal to m over 1, and then we just multiply fractions going straight across. So 1 times m is m, and n times 1 is n. Now, all I did was I just went in this direction. So we had the m over n, and I rewrote it as 1 over n times m. Okay, now this is just going to be a little rewrite. And this is also using our properties of exponents. So we know that if we raise a power to a power, that's the same as multiplying them together. Now, this time I had them multiplied together. So I said, well, I can just rewrite that as a power to a power. So we're using this property that we looked at. If you have, like, I'll change the, okay, is a times b, except what I did was I went in this direction. I had a times b and said, well, I'm just going to write that as a power to a power. Now, what is x to the 1 over n power? Well, I'm going to go back and use this property right here. Okay, and that's equal to the nth root of x to the first power. And what is x to the first power? Well, that is just, sorry, that's an m, is just x. And there we go. So if you look at this from one end to the other, we used all facts that we have established, properties of exponents, changing stuff over. Like we have used all of that we know is true, and we have like developed an argument that these are the same. So that is our final useful fact. Now, why is it useful? So I want you to consider this problem for a moment. I did this one out earlier to illustrate it. So there are two ways to do this problem. And if you're looking at it and you're like, oh, well, order of operations, okay. And so I'm going to work this out two different ways. So I've got the cube root of 8 to the 4th. Now, I don't know what 8 to the 4th power is off the top of my head. So I've got to go grab my calculator, and I'm going to do 8 to the 4th power, and that is going to tell me 4,096. And now I have absolutely no idea, like, is that even a perfect cube? Like, can I do the cube root of 4,096? So I've got to go grab my calculator again and do the cube root of 4,096. And it does tell me that that is 16. So 16 to the 3rd power, which is not something most of us would know. And I'm just going to go ahead and label that with yuck. Okay, now watch this. This is why it's useful. Okay, so I'm going to take the same problem and I'm going, I don't know if you could hear that. That was my cat jumping off a windowsill. She has knocked my basil plant on the floor twice today, so she's having a day. But watch what I'm going to do. I'm going to take that 4 and say, well, that 4 doesn't have to be under the radical. I could write that 4 outside the radical like so. Now the cube root of 8, I actually do know that is 2, because 2 times 2 times 2 gives me 8. So that is 2. And now my answer is 2 to the 4th power, which is another one that I know. 2 times 2 is 4, times 2 is 8, times 2 is 16. And I'm gonna write much better. Okay. So essentially it allows me to do that one in my head. And that little fact can give you some flexibility so that you're not reaching for your calculator and tangling with numbers like 4,096 because nobody likes that anyway. So that is why it's useful. Okay, so that wraps up the lesson. Don't forget to like and subscribe if you found this video helpful. Drop a comment to engage or ask a question. And please, please, please check out the practice set for this lesson. You want to see what problems of this type might look like and whether or not you would be able to execute them. I'll link it in the description box and below for you. And I hope to see you in a future video.